In this lecture, we shall be talking about IP version 6, which is the latest version of the IP protocol. Now, earlier we have looked at the so called IP version 4, which is more conventional and traditional. Now, IP version 4 has some drawbacks, which has led the designers of these protocols, internet protocols, to come up with a newer IP version. So, in this lecture we shall particularly see what are the drawbacks of the older version IP version 4 and what are the new features this IP version 6 incorporates. So, in this lecture we shall be talking about some of the features of IP version 6 protocol, the datagram format in IP version 6 and how certain kinds of address translation are carried out. Okay. So, let us look at the overall scenario first. Now, the first thing is that, as we have repeatedly said, this TCP IP forms the backbone of the internet that we see today, and IP protocol is most crucial in the sense that all packets that flow through the internet, they are routed using the IP protocol. So, IP ensures that packets reach the intended destination correctly. Okay. Now, as I had mentioned, this IP version 4 is more widely used today, but there are a certain number of drawbacks in this protocol. So, once we identify what these drawbacks are, then we can appreciate that what kind of enhancements were needed to enhance the capabilities, and that is how this newer version IP version 6 has come. This is also sometimes known as IP next generation, IP-NG. Okay. These both names are used interchangeably. Now, problems with IP version 4 are as follows. The first and most important problem is that we are using 32-bit IP addresses. 2 to the power 32 is how much? Close to 4 billion. But you see, with the huge proliferation of devices that are getting connected to the internet today, we are now in an age where we are talking about internet of things. There will be a large number of very simple devices, they will also want to get connected to the internet. So, how come we give unique IP addresses to everybody? This 4 billion is a rather small number by today's scenario. Okay? So, this cannot satisfy or support the kind of internet growth that is being projected, right. This is one. Secondly, there are many applications. You see, there are numerous streaming applications today, streaming audio, streaming video, streaming news and so on and so forth. They need some sort of a real time response, like something is happening, you are watching it live, let us say. Now, you will not like if there is a 10-second pause in between and then the video again starts to play. That is not acceptable in terms of the quality of service, right. So, there are such applications which are increasing day by day, where you need real time response. Real time response means the delay that you encounter must be within some tolerable limit. Now, what is that tolerable limit? It depends on the application, of course. Okay. So, for this kind of real time response, one requirement is that you should not change route very frequently, because we mentioned that IP uses some kind of dynamic routing and packets may follow different paths at different times. Now, if we consider the packets that correspond to a video stream, the packets are following one path, suddenly the packets start following another path which is a longer path, the delay will increase. Okay. So, that kind of variable delay may not be desirable for such real time applications. Secondly, there are some scenarios that are coming up where you need more complex addressing and routing capabilities. Like you recall in IP version 4, you have a 2 level routing, you have a network, you have a host. Of course, within the host you forcibly you used a subnet and introduced a third hierarchy, but that is just within the host address space available to you. But IP version 6 allows more number of levels of addressing, which becomes more flexible, and of course, it will get more complex. So, main features of IPv6, few of the features are borrowed from IPv4, whatever was there, same thing is carried forward. First such thing is connectionless. IP version 4 was based on datagrams, IP version 6 is also based on datagrams, which is a connectionless protocol. So, each datagram are routed independently and each datagram will contain destination address, so that the intermediate routers can take proper and informed routing decisions. Okay. And just like IP, if you see in IP there was a time to leave field, it told you what is the maximum number of hops a datagram can take before it will be discarded. At every hop the TTL field was decremented by 1. So, whenever it reaches 0 the packets gets discarded. Similarly, here also the header will contain a similar field maximum number of hops that a datagram is permitted to take, because you see you have some estimate regarding the maximum number of hops you require to reach a destination. If you find that even within that number of hops you are not able to reach, it means there is some problem in the network, maybe your packet is following a circular path in a loop, it has got stuck somewhere. So, in that case you discard the packet. And some of the other general characteristics like fragmentation and so on, those are also retained. Fine. Now, let us talk about the new features which are interesting. The most important feature is that the number of bits in the source and destination IP address is increased. Earlier it was 32, now it is 128, which means I can use up to 2 to the power 128 that many unique addresses. Now, how large is this 2 to the power 128? This is something you can actually calculate and find out. This is a decimal number which will be having maybe 45 digits, 45 digit decimal number, which is huge. But how huge is that? Just imagine you think of the surface of the earth. Just assume that I want to assign IP addresses to devices on the surface of the earth. 2 to the power 128 is such a large number that on every square meter on the earth's surface, you can assign about 6 into 10 to the power 23 unique addresses. So, this number is indeed huge, and it is expected that this will never be too small in the foreseeable future, right. So, this 120 bit is good enough, quite large. And another difference is that in IP version 4 there was a header and the header was fixed. So, whatever packet information the packet carried, it used to be put in the same header. But in IP version 6 what it does, it uses a series of fixed length headers. Depending on what you need, you add optional headers. Like if you do not need fragmentation, you do not use fragment header. If you need, then you add a fragment header. So, there will be multiple headers which will be connected in a linked list as part of the IP version 6 header. This is the basic concept. Okay. So, a datagram in IP version 6 will consist of a base header, that is the basic header, which will contain, for example, the source and destination addresses, and followed by optional extension headers. There may not be any, but there can be several. Okay. There are some additional features also, like as I said, for real time traffic there are some additional features which have been included in IP version 6. Like it is possible for two ends, two hosts to agree on a high quality path. Suppose I am viewing streaming video and I tell that, well, I want a guaranteed bandwidth of 512 kilobits per second. So, they will agree along with the intermediate routers to provide you with a dedicated path, a path through which you will get dedicated 512 kbps of bandwidth, so that you can receive the streaming media without any disruption, right. And all datagrams will follow this path. So, you see this is a slight deviation from the connectionless approach that IP version 6 also supports. For real time traffic, you have something like a connection oriented concept coming in. Okay. So, it is like a hybrid now. It is not a pure datagram approach. Sometimes when you need to have quality of service guarantee for real time applications, you may also specify the path which the datagrams will follow. Okay. And the next thing is that there are some new kinds of addressing which has come up. Like earlier there were addressing like host to host addressing, you are sending to a particular host, or broadcast sent to everybody. But now there is a new addressing mode called anycast addressing which have been introduced. Anycast means there are a set of computers, I am telling you send this message to any one of these. Okay, I do not specify which one, but any one of these. So, if it reaches any one of these, I am happy. This is referred to as anycast address. Okay. And also this provides for dynamic assignments of IP address, it can change over time, these facilities are there. So, IP datagram format, as I said, there can be multiple extension headers. The general picture is like this. It starts with a base header which is 40 bytes in size, but there can be multiple extension headers. The size of the extension headers can be different, and at the end you have the data. Because typically let us say TCP is running on top and below you have this IP version 6 running, IPv6. So, TCP will be sending you some message for transmission. So, that PDU, protocol data unit, transport layer protocol data unit, that is the message, will be appended with the IP headers whatever they are, and they will be sent as IP packet. Okay. Now, the base header, those 40 bytes will be having a fixed structure like this. You see some of the fields are somewhat similar to means IP version 4, but because of the change size of the addresses, you see source address and destination address are 128 bits long. Well, 128 bits means how many bytes? 16 bytes. You have 16 bytes here, you have 16 bytes here. Version is 4 bits. This is version 6. So, this will contain the number 6, 0, 1, 1, 0. Priority, you can specify a priority in the packet now, which in version 4 is not possible. Higher priority packet will move faster, router will give higher priority to those. Flow level, this is again concerned with flow control, some additional fields or information are there. I am not going into the detail of all of them. Then comes the payload length, which is the size of the total packet. Next header, I said that there will be a base header and there can be a number of extension headers. Okay. Now, there will be a field here which will be pointing to the next header. This will be pointing. So, this will be like a linked list. So, this next header field will contain the information that whether there is an extension header following this or not. If there is, then it will contain what type of extension header, and if it does not contain any more, then it will contain some delimiter indicating that there is no more extension headers. And this hop limit I told you about, just like time to live, that field is also there. This is the basic header in IP version 6. Now, talking about the fields I have already mentioned, let me go through this quickly. This version I told you about, this is a 4-bit field. IP version 6, it will contain the value 6, which in binary is 0 1 1 0. Priority specifies the routing priority class. Higher priority packets will be handled faster by the routers. Flow level, this is particularly used for real time application, where there are applications that require performance guarantee. So, flow level contain relevant information. This will contain some specific ID or code which will allow the packets to follow this a particular path, for example, right. Payload length is the total length of the extension header plus the transport level protocol data unit, that means the data you are sending. Next header, as I said, it is a pointer to the next extension header. It identifies the type of information that immediately follows the current header. It can be an IP extension, or it can be the actual PDU, TCP or UDP, that means the data. Hop limit, similar to IP version 4, it is decremented by 1 at each hop, and the addresses are 128 bits or 16 bytes or octets. Okay. So, pictorially it will look something like this. This is one example. Suppose this is a IPv6 packet which does not contain any extension header. So, in the base header the relevant fields are there, and the next header field contains TCP, which means it will know that whatever follows the base header is the actual TCP PDU which is carrying the data to be transmitted. Take this next example where there is one extension header. So, base header will contain an information next equal to route. It tells it has an extension header which gives you some information about route, maybe it is a source routing or specifying the route to be followed. And in the next header, this extension header, there will also be a next field which will tell TCP, that means this will be the actual TCP data. So, here there can be multiple such headers. So, this next pointer will be following these headers one by one. Okay. Now, the important kinds of extension headers which are there, they are summarized here. There can be a routing header, as you are seeing here. Routing header permits source routing. Now, I am repeating here what source routing actually means. Now, in a conventional packet routing, what happens? There are routers, a packet arrives at a router, the router looks at the destination address, looks at its own routing table and makes a decision where to forward this packet. So, it finds out which is the next router I have to send this packet, so that it can reach the destination correctly, or if it is destined to a host in my same network, I can directly send it to the network, to that host, directly send it to that host. Source routing means the person who is generating the packet, the host, directly tells that which sequence of routers must be followed for my packets. Because I know that this is a good path, the speed is high, so my packet will go faster. So, if I know that, I can specify that entire information as a routing header, and this is what is meant by source routing. The source is specifying the route, which path to follow, right. Second comes the hop by hop options header. Well, you can specify, this again depends on some applications, that every hop means actually whenever you move from one host to the other, you can check for certain conditions. Depending on that, you can decide whether to forward the packet, not forward, or do something else. Then for fragmentation, you have fragment header. This will contain information just like in IP version 4, which helps in fragmentation and reassembly, some flags, fragment offset, okay, and so on. And to ensure packet integrity, there is also an authentication header, where you can implement some kind of hash function. Well, we will be talking about hash function later in this course. These hash functions are used for authentication purposes. Well, authentication means, suppose I am a router, I have received a packet from some other router X. Now, there can be two scenarios. One, the router X is actually sending the packet I am getting is actually coming from X, or it may so happen that some kind of a malicious entity, it can be a hacker or some other node which is trying to send some, you can say, illegal packets to my network, is sending a packet in such a way that the source address is the same as X, but it was not sent by X. This is what is meant by authentication. I must be sure that whatever I am getting is actually coming from the person or the node which it is claiming as the source. That is authentication, right. And here, as I told, all the extension headers are changed in a linked list using the next header field, which is present in the base header as well as all the extension headers. Now, about fragmentation, just as I mentioned, this IP version 6 fragmentation is similar to IP version 4, but unlike IP version 4, where the additional information about fragmentation was put inside the same header, here we are using a separate extension header. Okay. So, when a fragment the idea is that when a IP version 6 packet, let us say there was a packet which had a base header, let us say BH. When it gets fragmented into two pieces, the scenario will be something like this. This base header will be copied to both the fragments. And there will be a fragment header containing relevant information. These are extension header. This will be added to the two fragments, and the data, one part will come here, the next part will come here. This is how fragmented packets will look like. Now, talking about IP version 6 addressing, as I told you earlier, that it introduces a new kind of addressing called Anycast. So, here the different addressing types are summarized. Here there is no concept of classes, just like IP version 4, there was class A, B, C, D, E we are defining, but here there is no concept of address class, classless. You specify a prefix length very similar to CIDR, classless internet domain routing, that how many bits you will be using for the network and how many bits for the host, that you specify here, and that introduces a lot of flexibility. Broadly, 3 classes of addresses are supported. One is a unicast address, which means it is a directed address of a particular node in the internet. That means, you are sending a packet to a particular computer, that is a unicast address. Multicast or broadcast. Multicast means you are sending the packet to all members of a given set. You can say that I am sending a packet to a subnetwork, it should go to all the computers inside that subnetwork, that is a multicast address, right. So, it must be delivered to every member of the set. Set is usually a network or a subnetwork. Then you have this new address Anycast, where it says the packet will be delivered to exactly one of the computers in the set. In multicast it was delivered to everybody, but here it is delivered to exactly one. And now the way these 128-bit addresses are specified. For IP version 4 you use the dotted decimal notation, you recall, but 128 bits is too long. If you use the dotted decimal notation after 8 bits, there would be 16 such numbers separated by dots. So, in IP version 6 they have come up with some kind of a shortcut notation. There is one thing to observe, that in this 128-bit address, which is pretty large, there are many bits in between which are zeros. A large number of these 128 bits are often zeros. Okay. So, we use something called colon. Instead of dot, we use a colon hexadecimal notation. Like you see, this is an example. Instead of decimal, we are using hexadecimal. Each digit represents 4 bits. So, 128 divided by 4 is 32. I use 30, I need 32 hexadecimal digits. See 1, 2, 3, 4, 5, 6, 7, 8. 8 into 4 is 38. So, each entity between 2 colons represent 4 hexadecimal digits. Like for example, here I mentioned 3DC. 3DC is not 4, I mentioned only 3, it means there is a 0 before that. Similarly, I had mentioned only 0 here. Only 0 means this is all 0, 16 zeros. 2D means there are 2 hexadecimal zeros before that. So, like this you can specify. So, you can write it like if there are a large number of zeros in between, which is often the case as I told you, you can either write it like this, or you can even use a shorter version. The beginning is non-zero, the ending is non-zero, in between everything is 0. You use 2 colons side by side, it will indicate that everything in between are all zeros. Okay. So, these are some ways to express the IP version 6 address in a compact fashion. Now, talking about the 128-bit address, you see this 128-bit address is typically separated using a number of hierarchies. The last 64 bits here, this specifies something similar to the host address part in IP version 4. It talks about some kind of unique addressing inside the network that you are addressing. Now, it can be this interface ID can also be based on the hardware MAC address if you want to. Typically, hardware MAC address are 48 bits in size and they are unique. You can use that same MAC address here if you want, or if you want, the network administrator can assign sequential numbers 1, 2, 3, 4, 5 like in a normal IP version 4 address numbering. And there are several other hierarchical fields, site level aggregation, next level aggregation, top level aggregation. Now, what this means, it may depend on from means one place to another. like at the top level it may indicate country, for example, that which country the network belongs to. Next level may indicate within that country which internet service provider is providing you the connection. The third level can provide some other hierarchical information, that means within state level or district level some information. So, you can have this kind of hierarchical address definitions which is very flexible. Depending upon your need, you can define these fields, but if you do not want, some of these fields can be left zeros. Okay? And these unicast address always starts with 001. Okay? This is what it looks like. This is just an example I gave for unicast address. Now, you see most of the networks today are IP version 4 networks. Now, we are saying that IP version 6 is required, we should migrate to IP version 6 whenever we can. Now, there are some incompatibilities, the packet sizes, packet formats are all different. So, you can have two this kind of scenarios for compatibility. One is called IP version 4 mapped IP version 6 addresses. This says within a host you install both IPv4 and IPv6 software. So, a host can support both IPv6 and IPv4, and that kind of a host is wanting to communicate with another host which supports only version 4. In that case, what is done? And if the packet which is being produced is a IP version 6 packet with IP version 6 address, then you generate some kind of an IP version 6 address which is formed like this: 80 zeros followed by 16 ones followed by a 32-bit IP version 4 address, because the person you are sending to, that is a IP version 4 network, which means it will have 32-bit IP addresses. So, this 128-bit address that you will have to prepare, the last 32 bits will contain the actual IP address of the destination, IP version 4. Then there will be 16 ones, and in the first part there will be 80 zeros. This is the convention which is followed. So, any address like this will mean that this is an IPv4 mapped IPv6 address, where the last 32 bit is actually representing an IP version 4 address. Okay. Similarly, you can have another option which is called IP version 4 compatible IP version 6 address. Here it is something like this. Suppose there is a network running version 6, there is another network running version 6, but in between there may be routers through which the packets are flowing, they may be version 4 compatible. So, how will these version 6 packets flow in this network? So, here you use something called tunneling. This IPv6 packets which are coming, these are the IPv6 packets. You create an IP version 4 header on top of it and create an IP version 4 packet. Let the IP version 4 packet flow through this network. This we are called tunneling. That means, a version 6 packet is tunneling through the network encapsulated inside a version 4 packet. That is the idea. And here the way we specify the address is that 80 zeros followed by 6, that means 96 zeros followed by the 32-bit IP address. That means, when you are sending this packet to this intermediate router, it is a version 4 network, which means it will be having a 32-bit address, right. So, that address you specify like this: 96 zeros followed by the 32-bit address. Okay. So, this is what tunneling is all about, which was used in the previous case. So, here diagrammatically it is explained. So, you have an IP version 6 host which is generating an IP version 6 packet. Then you have to send it to IPv4 router. What you do? You append an IPv4 header before it. So, the whole thing becomes an IPv4 packet. This IPv4 packet gets routed through an IPv4 network and it reaches the final destination. Now, in the final destination, this packet is stripped out and this IP version 6 datagram is brought out and it is delivered to the IPv6 host. This is what is meant by tunneling, right. So, talking about transition to IPv4 to IPv6, due to the incompatibilities there are challenges, but there are broadly 3 approaches you can think of. One is you implement both IPv4 and IPv6 protocols in the router or the gateway. So, that if someone wants to use or send IPv4 packets, it can be handled, V6 packets can also be handled, something like that. You can use tunneling just like I mentioned. So, IPv6 datagram can flow through intermediate IPv4 networks using tunneling, using encapsulation, or you can do some header translation. An IPv6 packet you can translate into an IPv4 packet, and on the other side you can again translate it back to IPv6 packet. But the problem is that many of the features IPv6 supports which were not there in IPv4 will get lost once you translate it into IPv4 packet. Okay. So, this has very limited use. So, with this we come to the end of this lecture, where we talked about some of the salient features of the IP version 6 protocol. Now, in the next lecture we shall be looking at various examples where we shall be showing you how routing tables are constructed for specific networks, how packets are handled by the routers, how packet forwarding takes place, subnetting, CIDR, all these things that we have studied earlier, we shall be illustrating through some examples. Thank you.